Welcome to this complete feature engineering tutorial for data science and machine learning. In this session, we are going to cover all the important feature engineering techniques that are used in real-world machine learning projects. Feature engineering is one of the most critical steps in building high-performance models. In fact, a well-engineered dataset can outperform even complex algorithms. Let's begin. Feature creation/construction. Now let's talk about feature creation, also known as feature construction. Creating new features from existing ones helps the model capture patterns better. Raw data is rarely in the best format for machine learning. For example, from date columns, we extract time-based patterns such as month, day of week, or whether it's a weekend. We also create behavioral signals, ratios like income per age, and interaction effects such as age multiplied by income. In real-world projects, domain knowledge plays a very important role in feature creation. Understanding the business problem helps us design meaningful features that improve model performance. Feature transformation. Next is feature transformation. Transforms make features more suitable for machine learning models. This includes scaling numeric values, normalizing distributions, or binning continuous variables. We use scaling because many machine learning algorithms assume that features are on a similar scale. We also use log or box-cox transformations when the data is skewed. Distance-based models like KNN and SVM fail without scaling because they rely on distance calculations. So transformation ensures fairness between features and improves model stability. Feature encoding. Now let's discuss feature encoding. Machine learning models cannot understand text categories like city names. They only understand numbers. So we convert categorical data into numeric format using techniques like label encoding, one-hot encoding, and target encoding. However, we must be careful. If we label encode cities as New York equals 0, Chicago equals 1, and Los Angeles equals 2, the model might incorrectly assume Los Angeles is greater than Chicago. That's why for non-ordered categories, we use one-hot encoding. Choosing the right encoding method is extremely important for model accuracy. Handling missing data. Now let's move to handling missing data. Missing values are very common in real datasets. Models generally cannot handle null values, so we need to address them before training. Common strategies include imputation, where we replace missing values with mean, median, or mode. We can also create a missing flag feature to indicate whether data was originally missing. In real projects, median is often better than mean for skewed data. Sometimes missing values themselves carry information, so adding a missing indicator can improve performance. Feature selection. Now we move to feature selection. Selecting the most important features reduces noise and improves model performance. Too many features can cause overfitting, slower training, and multicollinearity. There are three main approaches. First, filter methods, which use statistical techniques like correlation, chi-square, and mutual information. Second, wrapper methods, which use model performance to select features. Third, embedded methods, where feature selection happens during training, like in lasso regression or tree-based models. Random forest feature importance is a common example of embedded feature selection. Feature selection improves model interpretability and efficiency. Polynomial/interaction features. Next, we look at polynomial and interaction features. Polynomial features help linear models capture nonlinear patterns. For example, if the relationship between income and target is curved, we may include income squared. Interaction features like age multiplied by income allow the model to capture combined effects. These techniques are especially useful when working with linear regression models that cannot automatically learn nonlinear relationships. Dimensionality reduction, PCA. Finally, let's discuss dimensionality reduction using PCA. PCA reduces the number of features while retaining most of the variance in the data. This is particularly useful when features are highly correlated. For example, in text embeddings, we may have 300 or more features. In image data, we may have thousands of pixel values. PCA compresses this information into fewer components, making training faster and reducing noise. Dimensionality reduction improves efficiency without losing significant information. To summarize, feature engineering is the heart of machine learning. It includes creating meaningful features, transforming them properly, encoding categorical variables, handling missing data, selecting important features, and reducing dimensionality. Mastering feature engineering can dramatically improve your model's performance, sometimes even more than changing the algorithm itself. Thank you for watching.